Okay, students. So, have you become familiar with this tool, Vivado? Tell me if anyone is having any issue, anything related to the tool or to the process that we are doing with this Vivado. You can ask. Yes. Who is this? Sudesh Kadam. Sudesh.
Yes, sir.
Sudesh, did you practice?
Sir, I have problem, sir. I don't have any laptop, so I'm going to it
You
through
don't
online, sir, on YouTube.
online YouTube. Hmm.
Uh,
Okay, for those people who are not having a laptop, okay, it will be a bit difficult. So that at least you go through the theory part, okay, and if you still want to, practice with the something, then there's a website which provides this online kind of thing, online simulation kind of thing. I EDA Playground, I think EDA Ground dot com or dot org. Just let me see. EDA dot com com. Okay, I've given uh, this site name here, edaplayground.com. Okay, you can go to this site, and for using this, you will have to register on this. Okay, so try to register. If you are able to register successfully on this, then you can start using this online platform. So this is basically providing an online platform where you can write the code and get it simulated. Okay, simple things are there. Just try to refer to this. Try
yes,
to
sir.
use this. Okay, and in future I will also share some more links regarding those people who are not having laptops with them, so that they can still get benefited. No, then Prayas Das Patnaik. Prayas Das Patnaik.
Yes, sir. Hello.
Yeah, yeah, Prayas. What happened? Means what did you practice? Did you do this? The first experiment?
Sir, excuse, hello, sir.
Yeah, hello.
Hello.
I'm hearing. Tell
Yes, sir.
me.
I am not having my laptop. Yes, sir. I am not having my laptop. I left it in hostel.
Oh, many people are facing this. Then what are you doing? How are you? Are you referring to some online lectures or what?
Sir, sir. Now only I knew about this website edplayground.com. Then I will look into it.
Uh, okay, try to use this. Try to use this. Okay, and then so many people are not having laptop. They left their laptop at their hostels. This Swasti Subha
Y-
Shweta.
Yes, sir.
Do you have your laptop or not?
Yes, sir, but I have not practiced it. I was figuring it out, but I couldn't. So I'll try this website, sir.
Why, if you are having laptop, then you should do it on laptop. No, no matter. Hmm?
Yes, sir. I tried, but it is like the old version. So, so I
Which
was
version?
looking for. So mine it is Windows 8. So I was facing problem with it.
What problem? Tell me now.
Sir?
What problem you are facing, Swasti?
So for this in like starting that program.
You have installed it properly?
No, sir, I couldn't install it. I was trying, but then I referred some YouTube videos also. But my laptop is showing some problem. Like other websites also, some. Um, I was trying for coding that is also showing problem. So I think it is like something with my laptop.
I think version on Windows 8 also. It is working fine on 8 also. No issue.
Okay, so I will try this.
If you face
Like
any,
try
if you
try
face,
coding.
if you face any problem, then
Yes,
tell
sir.
me.
I will contact you, sir.
जीवन ज्योति, जीवन ज्योति boy. Yes, जीवन ज्योति boy. जीवन ज्योति, unmute yourself.
Hello, sir. Good morning, sir.
Good morning, जीवन ज्योति.
Yes.
What about you?
Sir, I have no
Did you practice
laptop.
or what? Oh, many people are not having ना.
Yes, sir.
चलो ठीक है. I will start today's class. Okay, so today I will go through another simple circuit known as full subtractor. You have read about this also. Okay. So I will start sharing my screen. Okay, students, is this visible? Is the slide visible? Anyone can confirm?
Yes, sir, it is visible.
Okay. Okay, so let's start with this topic. Okay. So if you are familiar with full adder, then full subtractor will be a very simple thing because it is almost similar to full adder circuit. It is very similar to full adder circuit. So like we can say that a full adder is a combinational circuit. It's a combinational circuit, okay, because it does not contain any memory part. It does not contain any flip-flops or any other memory element inside it. So we call this a pure combinational circuit. Okay. So it's a combinational circuit that performs subtraction of two bits. One is minuend and the other is subtrahend. Taken into account borrow of the previous adjacent lower minuend bit. Okay, so basically it is performing the subtraction between two bits. Okay, and also it takes into account the borrow that's coming from the previous bit. Okay, so the inputs are three in number. Okay, uh, the first input is A, let's say A. Second input is B, so it wants to perform A minus B, and B in is the borrow that will come from the previous bit. Okay, and hence it will have three inputs, and it will produce two output. Okay, the first is the difference D. Let's say D is the difference part. Okay, and B out is the borrow output borrow. Okay, and this is the simple block diagram of a full subtractor circuit. Okay, but the operation will be more clear if we refer to the truth table of this circuit. Okay, so look at this. This is the truth table of a full subtractor. So for example, these are the inputs A, B, and input borrow, and these are the outputs D for difference, and B out is borrow output. Okay, so let's start because there are three inputs, so we can have basically a total number of 8 conditions. Okay, so right from 000 to 111. So let's start from 000. A is 0, B is 0, B in 0. So 0 minus 0 is basically 0, and borrow output will also be 0. Okay, now second condition, 0 minus 0 is 0, and 0 minus 1 will be 1, the difference is 1, with an output borrow of 1. Okay, and in this case 0 1, 0 minus 1 is 1, output borrow is 1. Okay, and here 0 minus 1 is 1. Okay, and 1 minus 0 is again 1. Okay, so so the difference becomes 1, and output borrow was produced when we subtracted 1 from 0 here. Okay, and that output borrow will come here. Okay, now here in this case 0 1 1. Okay, so 0 minus 1 will be, the difference will be 1, and the output borrow will also be 1. Okay, and here 0 minus 1 produced 1, and from that difference 1 we will subtract this input borrow 1 again, so 1 minus 1 will become 0, and we still have a output borrow that was produced in the first case when we subtracted 1 from 0 here in this case. Okay, so here 1 minus 0 is 1, output borrow is 0. Okay, and from that difference 1 minus 0 again is, the difference still remains 1, and output borrow is 0, right? Now here look at here 1 minus 0 is 1, and 1 minus 1 is 0, so the difference becomes 0. Okay, and what about output borrow? So 1 minus 0 does not require any output borrow. Okay, 1 minus 0 is 1, and then again from 1 minus 1, again it does not require any output borrow, so the difference and output borrow still remains 0 and 0 here in this case. Okay, look at here 1 1 0. So 1 minus 1 difference is 0, output borrow is 0. Okay, and from this 0 difference, 0 minus 0 is 0, and output borrow was still 0, so D is 0 and output borrow is 0, right? Look at here 1 1 1. So 1 minus 1 is 0, output borrow will remain 0. Okay, now from this difference of this result 1 minus 1, that is 0, from this difference result 0, subtract this 1, so 0 minus 1 will be 1, and it will require an output borrow of 1. So in this case the difference becomes 1, and output borrow also becomes 1. Okay. So is this truth table clear to all? Yes. Okay, so if this truth table is clear, then let's proceed further. Okay, so after understanding the truth table, we would like to form the equations and equations for the uh, output signals, that is D and output borrow here in this case. Okay, and we know that for getting the output equations, one way is to get the terms corresponding to the cases when it is 1. Okay, so D is 1 here. It means that for this case A is 0, B is 0, B in is 1, so it will be A bar, B in the first term, and for the second term when D is 1 here. Okay, this will be A bar, B and B bar. Okay, and similarly we can form the other terms corresponding to D1 here in this case and D1 here in this case. So we will have 4 terms for this D. Okay, and then after getting those 4 terms, try to simplify that particular Boolean expression. Okay, using the Boolean laws. Okay, and similarly the equation for B out will be formed according to the condition when B out is 1 here. So it is again 1 for 4 times. Okay, so it will again contain 4 terms in its equation. Okay, so let us see those equations. This is the equation. So look at here, the equation for difference. Okay, so the first term is A bar B in plus A bar B in bar plus A B in bar B bar plus A B in. Okay, and when you simplify this equation using Boolean laws, okay, you will get this final term, this final equation, and we can say that finally D can be written as equal to A XOR B XOR B in. Okay, or A XOR B XOR input borrow. Okay, and we can very easily say that this is the same equation as that of a full adder. Okay, so if you remember full adder circuit, full adder part, then this equation corresponds to uh, which particular signal from the full adder output. uh, we can say that the difference equation is same uh, equation as it was for the sum output of full adder. If you remember, the sum output of full adder was also A XOR B XOR C in. Okay, and here it is also in the terms of XOR gates. So A XOR B XOR B in. Okay, so this is how you can try at your rooms, at your homes. Okay, try to simplify this and verify whether you are getting this particular simplified term or not. Let's try to verify this. Okay. Then similarly, we can get the equation, the simplified equation for output borrow. Okay. And we will start again with the truth table. Okay. You can do the simplification either by using the Boolean laws, or you can also use the simplification. You can also use this K-map reduction technique, the Karnaugh map, for reducing or for simplifying any uh, equation, Boolean equation. Okay, so you can either use a K-map reduction technique, or you can also use those Boolean laws for reducing any particular logical equation. Okay, so in this case you can reduce it to basically two forms. Okay, in the first case we can say that our output borrow or B out can be stated as, in simplified form, as A bar B in plus A bar B plus B B in. Okay, or we can also simplify this in another form like this. Okay, where we can say that B out is equal to B in into A XOR B bar, okay, plus A bar B, okay, plus A bar B, right? So either of these two equation, you can use either this equation, this term, or you can use it uh, either this equation for the design or for any other purpose, because the result will always come out to be same. Okay, although the terms are different, but the result will always be same. Okay, but we will see that one of these equation is particularly useful from designing point of view. We will see that thing, and we will also try to figure out that why one term, one equation is more useful in designing part as compared to the other equation, other term. Okay, we will see that thing. So meanwhile, can I ask that what was the equation for carry out from full adder? If you remember, what was the equation for carry
A
out?
XOR B XOR C. A XOR B XOR C.
A XOR B XOR C. Only this one?
That is for sum. What is for carry?
That was for some.
AB plus BC plus CA.
Okay, AB plus BC plus C, right. Okay, so C out was actually AB plus BC plus C, fine, right. So we got the equations for difference and output borrow in this case. Okay, and then the next step is to draw the logical diagram using those equations. Okay, so look at here. We are having three inputs. This is the first input A, second input B, and this is the third input borrow in. Okay, and let us start with this first output, that is a difference. Okay, now this is coming from here. So this point is actually this is an XOR gate. Okay, so this is A and this is B, so this becomes A XOR B. Okay, so this is particularly A XOR B, and the second input is coming from borrow in. Okay, and this is also an XOR gate. Okay, so this becomes A XOR B XOR borrow in. So the equation for difference is same as the equation that we obtained from the K-map reduction. Okay, this is simple, straightforward. Now looking at the borrow out, okay, it is coming from here. Let's start from here. So this is A, this becomes someone wants to join. Okay, so this point becomes a bar, okay, and this is coming from B, so this becomes uh, a bar B, okay, this particular signal is a bar B. And what about this signal? Okay, this signal is coming from the AND of these two inputs, okay, and this is the invert of this particular signal, and this is actually A XOR B. So this becomes A XOR B bar, and this is borrow in. So this point we can write as the AND of A XOR B bar, okay, and this is ANDed with the second signal, second input, that is input borrow, that is B in. Okay, and the final equation for borrow out will come out to be the OR operation, the ORing of this term and this term. Okay, and you go and verify whether you are getting the same equation for borrow out or not. Okay, so this is how we can draw the logical circuit for a full subtractor, right? And also this block diagram, using block diagrams we can also see that how particularly that why I am showing this diagram will become clear. Just let us see here that this difference part is coming from this. If you are having a half subtractor circuit, okay, because half subtractor is a bit simplified form, okay, like we are having half adder and full adder. Similarly, we are having half subtractor and full subtractor, okay, and half subtractor will subtract just 2 bits. It will not have any input borrow coming in, okay. So the equations will be simple, and it will be having 2 inputs and 2 outputs, okay. So for an half subtractor circuit, suppose if we are given with half subtractor, and then if the task is to build a full subtractor using half subtractors, then that is implementation of full subtractor using half subtractors. Then how to do it? You have got only half subtractor and one OR gate, okay, and no other gates are being given to you, and you are being told that implement a full subtractor circuit using half subtractors and one OR gate, okay. So this is how it can be done here. In this case, use the first half subtractor circuit here, okay, and feed the 2 inputs A and B here, okay. You will get one difference and one for borrow, output borrow for this half subtractor circuit, okay. The first difference will come into the input of second half subtractor circuit, and the third input, that is input borrow, will also come here, and you will get the final difference for the full subtractor coming out from here, okay. And the borrow of this particular half subtractor will come and feed into this OR gate, and this borrow is coming from the borrow out of the first half subtractor circuit, that is named as half subtractor circuit A, and hence it is called as borrow A, okay. And you OR perform an OR operation of this borrow A and borrow B to get the final output borrow for the full subtractor circuit. Okay, so uh, this circuit is useful if you are given with the half subtractor blocks, okay, and one OR gate. Okay, otherwise otherwise this circuit would be used most of the time. Okay, if the half subtractor blocks are not given. Okay, and remember that I told that one of these equations would be more useful. Okay, and uh, which equations we have implemented in the circuit diagram is, I think we had implemented this one. We had seen the implementation of this particular logical equations and not this one, not this one. Okay, so any idea, do you have any idea that why this circuit was chosen, why this logical equation was chosen? Although we could have implemented the uh, output borrow using this logical equation also. Okay, but I have chosen this one because this contains one XOR operation here. Okay, one XOR operation that performs the XOR of A and B. Okay, and we already have A XOR B coming out from the difference part, from the difference part. Okay, so that particular look at this difference. This is the difference signal coming out, and these are the circuitry that is producing that difference signal. Okay, and somewhere we require A XOR B. This is the point where A XOR B is coming out. Okay, and this signal that is being produced for producing a different signal, this intermediate signal can also be used for producing the output borrow part. Okay, so it means that this particular XOR gate becomes becomes a uh, common gate that is producing the uh, output for difference as well as borrow. Okay, so that we do not need to use two separate XOR gates. Okay, we are not we cannot what is the need of using two separate gates, two separate XOR gates, if it is also being produced, if it is already being produced inside difference block. Okay, so let us use this signal and connect this signal from this point. Okay, so because of this reuse of this gate, of this XOR gate, okay, between difference and borrow out, okay, I have shown this circuit uh, corresponding to this particular borrow output. Okay, and not this one, although it is equally right to implement this circuit also, this particular logical equation. There is no issue with that. You will still get the same input, same output. Okay, there is no harm in that, in doing that also. So students, any point from here, right from the definition to the truth table to the logical equations and to the circuit? Any doubts from here? You note down the equations. It is better if you note down the equation for the difference and for borrow out. Okay, now let us go to the designing of this, the simulation part of this using vivado tool. Okay, so I have already opened the vivado tool. Okay. And this is the full adder that we had done in the previous class. Okay, so that same project folder I will use for creating this particular logo. So I will not create any new project, I will continue using that same project. Okay, and keep in mind that one project may contain several, several design files, several source files. This particular project may contain many design files or many source files. Okay, the first design file, source file was full adder one, FA1. Okay, now I would add another source files. Okay, so I will click on this small plus sign here, add sources. So this time I will add or create again because you are familiar with this. So I will go a bit faster. Okay, add or create design sources. Next, then create file. So the name of the file, let's give full underscore subtractor one. Okay, again name full underscore subtractor one, and finish this. Okay, yes, and create one file, one verilog amp file for full subtractor. Okay, you double click on this, and this template file will appear like this. Okay. So this is the first line. Number 16 is line number 16 is module full subtractor one brackets. Now you can help me in writing for this. What should we write inside these brackets in line number 16? Yeah, students, what should be there? What should be here inside these brackets? What is mentioned here? Anyone?
Input and output named.
Yeah, what are the input and output signals? Tell me here. Let's say that we go with A, B, and the other one. What was the third input? Borrow input. Let's say this was B in. Okay, and the output was difference D, and the other output was
B out.
B out. Yeah, borrow out. Right. So this is called as the port listing. Just list the number, list the name of the ports. We are not declaring that which port is of what type. A B is input port, B in is input port, D and B out are output ports. So we are not specifying the type of that port. We are just listing the name of the ports. Okay. Now in line number 17, we will list out the type of the ports also. Okay. We know that A, B, and C in are input ports. Okay. So write the keyword here input, then A, B, B in. Okay, and we also know that D and B out are output ports, so the keyword is output, D and B out, and semicolon. Okay, right? Now the equations are to be written here, coded here. Okay, one way of using coding is to use the assign keyword as we had used in the case of full adder. Okay, so let us go with the same methodology. Assign D equals to, because A XOR B in. Okay, so what can I do is I can copy from here, from full adder, I can paste it over here, and A and B are same, only C in should be replaced by B in. So I will do it here. Okay, and it is fine. Then the assign for b out. B out. If you remember the equations, tell me the equation. I do not remember. Okay, what should come here? I don't remember. You tell me. Assign B out equals to,
Sir, A bar
what was the equation for B?
Sir, A bar B plus A bar B in plus B B in.
Yeah, tell me the second equation. Okay, let's go with the first
Yes,
equation. No issues. A bar
yes,
B.
sir.
Okay. How to write A bar? How to
Yes,
write A bar?
complement A.
Complement.
A.
Okay. A bar
B
B. Okay, this is the first term.
plus
Then
or
OR is, what is the symbol for OR? Vertical slash.
vertical. Yes, sir.
Yes. And then
Or A bar B and B in.
A A and B in.
Or
Then
or
OR
B and B in.
B
And
and
B
B in.
in. Yes,
Okay. B and B in. Okay, this is the equation.
yes, sir.
Just look at this. Check this whether I have written right or not. All of you, please check this equation. Okay, then this is the source file, right? And it seems to be okay. And if you want to verify this, whether this is right or not, we need to simulate this, right? We will have to simulate this. And for simulation, we need another file that's called as a test bench file. That is called as a test bench file. Okay, and we will have to create the test bench file so that we can perform the simulation of this particular design file. Okay, so there are two files, two separate files. One is design file and the other one is test bench file. Okay, design file will describe the circuit that you're designing, and the test bench file will help in performing a simulation of the design file. Okay, so let us create a design file. Okay, before that, one point here, because here under design sources tab, we are having two design sources. One is FA1 and the other is full subtractor one. Okay, and if you can see, if you can note that FA1 is highlighted, it is bold, written in bold. Okay, and there are three dots here. Okay, so it means that this is the top module right now. Okay, but I want to work with this full subtractor, not with full adder one. Okay, so if there are multiple design files, okay, under design sources tab, and there could be only one top module at a particular given instant of time. Okay, and that particular top module will be worked with. Okay, so I want to work with full subtractor one, so all the simulation, all the synthesis, all those things should be happening to this particular source file. So for that thing, I will have to set this particular file as the top module file. Okay, so what you can do, just right click on this and choose the option set as top, and now this has become highlighted. Okay, and these three dots are appearing here, so it says that this particular file is now the top module file, and whatever simulation, synthesis and other analysis will be done for this particular file. Okay, so keep this point in mind. So let us create one simulation file, simulation sources here, add or create simulation sources. Then give a file name here. I want to create a test bench file. So let's name this as let's say TB. Okay, TB underscore full subtractor one. Okay, This is a symbolic name that I am giving. You can give any name that you prefer. Okay, but choose a name that helps you in detecting that which particular circuit is being described by that name. It should help. Okay, so by reading this TB, I know that this is a test bench file. Okay, and underscore full subtractor one. So I know that this test bench file is particularly referring to this particular design file, which is named as full subtractor one. Okay, okay, okay. So then finish this. Click OK here, and yes, and the simulation file will be shown under this heading named as simulation sources. Okay, and which this one tb underscore full adder full subtractor is my current simulation file. So I will have to make this as the top module because I want to work with this. Okay, so again right click on this and set as top. Okay, so tell me, how do we write the test bench file? If you remember, line number 19, module tb underscore full underscore subtractor, and these brackets are left empty. Okay, then what do we do next? Next we list the ports as reg and wire. Okay, the ports are already defined in the design file, so I am copying and pasting from there, and the inputs are described as reg. Okay, and the outputs were described as wire. And why are these being done? It will become clear with time. Okay, so give some time on this in this semester, it will become clear. Do not worry about this. So we declare inputs as reg type, and we declare the output as wire type. Okay, then what do? We call the design file. Which design file we want to simulate, we should call that, or we should instantiate that particular design file. Okay, so this is the file that I want to call. I will call, copy and paste the name. Okay, the file name is full subtractor. And how do we instantiate file name? And give some space, give any instantiation name here. Okay, and then inside brackets you write down the name of the ports in the same order as it was for the design file. Okay, now here it means that this particular a is matched uh, with the a of full subtractor. Okay, this particular b is matched to the b of full subtractor. Okay, this b in is of this test file. Okay, this b in is different. Now this b in is matched to the b in of the full subtractor result file. Okay, now this d is the d of the signal output, uh, signal of the test bench file, this particular d. So this d is matched with the d of the subtractor. Why? Because we are calling the full subtractor here. Okay, so this is called this is how we instantiate file in verilog. And then the next thing is to give stimulus or give the signal values for which we want to verify or simulate the design file. Okay, now I will go to the test bench file of full adder. Okay, and there we had already done this thing. Instead, some copy from here and come here, and I will simply paste that thing here. Okay. So remember, I identified is initial. This is the beginning of initial, and it will end with and in line number 36. Okay, and inside the begin and the end, all the signal values should be stated. Okay, now we are using here three inputs A, B, and B in, right? So we can start from row 0 through 111. Okay, so look at line number 27. Okay, A is 0, B is 0, and C in is 0, right? C in is 0. And this hash 5 means, what does this hash 5 means? If you can remember,
Sir, delay.
yes, students, what is this?
Sir, delay.
Yeah, this is delay. This is a delay of 5 nanoseconds here in this case. Okay, this is a delay of 5 nanoseconds. Just a minute. So is there any problem with this line number 27? Is there any error that you can identify? What is the error associated with line number 27? Or it is error free?
We have to take B in instead of C in.
Yes. What? What is the
Sir,
error?
we have to take B in instead of C in.
Okay, right. We have to take B in because the signal that is defined here is B in, and here it is written as C in. So I'll have to replace all of these C by B. Okay. Now this becomes B in all. Okay. So look at here. This is the case for 000. This is 001. This is 010, and similarly this is 101, and this is 111. And this dollar finish will finish the simulation, so that after performing these 8 condition simulations, it will stop there. Okay, so this is the test bench file for this full subtractor, a simple test bench file. Okay, just save this, and look at here inside simulation tab, under simulation tab. This is our top module, tb underscore full subtractor 1. Okay, and because we had instantiated the full subtractor design in line number 23, and this instantiation is shown under this test bench name here. Okay, if I expand this instantiated design file is shown under this test bench file. Okay, so this is how you can verify that whether this file is fine or not. Okay, now I will go for the simulation. Okay, so after writing test bench file, I can go for the simulation. So here, look at here, left hand side, I can click on this run simulation and select this run behavioral simulation, and it will show you the simulated output for this particular design file. So this waveform window will pop up here. Okay, and look at here, I can bring all the different conditions in the same window. Look at here. This is look at here. This is the case when A is 0, B is 0, Bn is 0, okay, and D is 0, B out is 0. So now you try to match these outputs with your truth table outputs and try to verify. Okay. The second condition, look at here. Now here A is 0, B is 0, and B in is 1. For this case, this is giving us this D as 1 and B out as 1. Okay, now you try to match these outputs with the truth table. Similarly, you will try to match for each of these 8 cases. Look at here, 0 1 0. The D is 1, B out is 1. Try to match. Okay, the last state, when all are 1, A, B, B in are 1, D and B out are also 1. Okay, so you'll match these outputs with the table outputs, and if you are satisfied, you can say that the simulation output is fine, is okay for this particular design. And if the simulation output is okay, then we can assume that the code that we have done for this particular design is okay. The code is right, that we can assume. Okay. So after simulation, what do? After simulation, we perform the synthesis part. Okay. Now, whatever steps that we had done for full adder, okay, full adder, we had performed this run synthesis. Then we had done some simple analysis of the design. We had observed the schematic. We had observed the power consumption. We had observed the utilization, hardware utilization. Okay, so last three things that we had done for full adder, those things you will do for full subtractor here also. Okay, so this I am leaving you as your homework. So you go through this, design this full subtractor, write a test bench file, then run the simulation. Till this point I have done here. Then you run the synthesis part, and you analyze the circuit by analyzing its schematic, by analyzing its power, and by analyzing its hardware utilization. Okay, and after this you will run this RTL analysis. Okay, and you will open the elaborated design here, and under this category you will see the schematic, the elaborated schematic of this particular design. Okay, so there are two schematics basically associated with this. One is the synthesis schematic, okay, this one, and the other one is as this RTL schematic. Okay, and then you will compare the schematic, the two schematics. Okay, and then you should also compare the results, that is the power and hardware results for this full subtractor with that of full adder. Okay, you should compare the circuits, that which particular circuit is consuming more power, which particular circuit is consuming more hardware. Okay, so if you have the reports for all those circuits, you can compare those ones. Okay, is it clear that what you have to do? Students, is it clear? Students, so this I will ask in the next class. Okay, so take it seriously. The students who are having laptop with them, uh, they should do it. Okay, so the ones who do not have laptop at their homes, I cannot say anything to them because they are not having the facility. But the ones who are having laptop, they should at least try this. Okay, they should at least try this. Now you can ask me the things, the doubts, any queries related to this. Any doubts regarding this? No one is responding. So what should I understand? I assume that no one is having any doubts. Okay. Can I assume? Next topic. The next lab. Uh, take it as multiplier circuit. We had seen we had seen the adder, we had seen the subtractor. Then next we will do the multiplier. So now it will be a 4-bit multiplier. 4-bit multiplier. Okay. I am writing in the chat box 4-bit multiplier. Try to go through the theory part of this 4-bit multiplier circuit, a digital 4-bit multiplier. Okay, and how the architecture looks, and how can we design this using verilog. Okay, so in the next week we will meet in the same time as today is Wednesday. So next week we will start early. We will start from around 9 or 9:30. We will start. Okay, so that we can get more time, and we can communicate more. I will try to contact more students next week. So come with some preparations, at least the theory part. You should be prepared. You should have gone through. Okay, at least 50% you should understand by theory part, because if your theory is clear, then this lab becomes very easy. It is only about just some things about related to the coding. Okay, and coding you are already aware of. We have done the programming part already. You know, in your, I think you might have done programming in C language and Java and other things you might have done already. So from that background, from that backup, it becomes a bit easy in this case. Okay. And Aditya sir is here. Aditya sir. Hello, Aditya. Aditya sir was here, no?
Yes, sir. He left in between.
Okay. So regarding, I was asking about the copy. Have you are you preparing the reports for other labs? Yeah,
No,
students.
sir, not yet.
Okay, you are not writing the lab. Okay, okay, okay. ठीक है, I will try to clarify this in the next class. Okay, and if you don't have any doubts, you can give your attendance in the chat box. Okay, write your roll number and name. And we are also having one theory class from 12:20, I think. Okay, 12:20.